Right now, more than 15 billion miles from where you are sitting, a small spacecraft built in the 1970s is dying. Its power drops by 4 watts every single year. Its signal takes over 23 hours to reach Earth. If something breaks, no one can fix it. No rescue ship exists. No supply mission is possible. And Voyager 1 is not even close to leaving the solar system. The Oort cloud, the true outer boundary, extends nearly 2 light-years into space. At its current speed, Voyager will not clear it for tens of thousands of years. 30,000 years of drifting through a region so hostile, so remote, and so indifferent to human survival that the dangers most people imagine about space do not even begin to describe what actually waits out there. If this kind of deep science keeps you thinking, a like and a subscribe genuinely help us keep making these. It means a lot. Are you comfortable? Now, let's begin. There is a picture in almost everyone's mind of what it means to leave the solar system. You have seen it 1,000 times. A spacecraft crosses an invisible line somewhere past the last planet. The sun shrinks to a dot behind it. Stars stretch ahead. And then the ship glides forward into the unknown, heading toward another star, another world, another chapter of human exploration. It feels natural. It feels like the next step. And that feeling is one of the most dangerous misconceptions in all of science. Because almost everything about that picture is wrong. Not wrong in the way a fairy tale is wrong. Wrong in the way a map drawn by someone who has never left their house is wrong. The proportions are off. The distances are fabricated. The emptiness between things is not just underestimated. It is unimaginable in any honest sense of the word, and the danger that comes with crossing into that emptiness is not the kind of danger you see in movies. It is not an explosion. It is not an alien. It is not a meteor shower ripping through a hull in slow motion while an orchestra plays. It is something far worse. It is the slow, compounding collapse of every system and every assumption that made the journey feel possible in the first place. To understand why, you need to start with one very basic question that almost nobody asks. What does it actually mean to leave the solar system? Most people would answer instantly. You pass the last planet. You cross some boundary, you are out. But that answer reveals how deeply the illusion runs. Because the solar system does not end at the last planet. It does not end at the edge of the Kuiper belt. It does not end where Voyager 1 crossed the heliopause in 2012. The solar system extends far, far beyond all of those landmarks, and the true edge is so distant from the sun that it makes every other measurement in our neighborhood feel like a rounding error. Let us start with what people think the boundary is. The 8 planets of the solar system span a region that stretches from Mercury out to Neptune. Neptune orbits the Sun at an average distance of about 30 astronomical units. 1 astronomical unit is the distance from Earth to the Sun, roughly 93 million miles. So Neptune is about 2.8 billion miles from the Sun. That is an enormous distance. Light itself takes more than 4 hours to make the trip. A spacecraft traveling at the speed of the Voyager probes, roughly 38,000 miles per hour, would need over 12 years to cover it. And yet, in the context of the full solar system, Neptune is close, embarrassingly close. Beyond Neptune lies the Kuiper belt, a region of icy bodies, dwarf planets, and frozen debris that stretches from roughly 30 astronomical units out to about 50. Pluto lives here. So do Eris, Makemake, Haumea, and thousands of other objects that orbit in the cold fringes of the Sun's planetary domain. Most people, if pressed, would place the edge of the solar system somewhere around here. 50 astronomical units, maybe 60. Somewhere in the Kuiper belt, the Sun's grip loosens and you drift into the space between the stars. That is not even close. Beyond the Kuiper belt, the sun's influence continues in a form most people never think about. The solar wind, a constant stream of charged particles blowing outward from the sun at speeds ranging from roughly 700,000 to nearly 2 million miles per hour, pushes against the gas and dust of interstellar space. This creates a vast bubble called the heliosphere. The heliosphere is enormous. It extends roughly 90 to 120 astronomical units from the sun, depending on direction and the sun's activity cycle. Its outer boundary is called the heliopause. This is where the solar wind can no longer push outward against the pressure of the interstellar medium. It is the point where the sun's direct material influence ends and the environment of the galaxy begins to dominate. This is the boundary that Voyager 1 crossed on August 25, 2012, at a distance of about 122 astronomical units from the Sun. Voyager 2 followed on November 5, 2018, at roughly 119 astronomical units. When those crossings happened, headlines around the world announced that the spacecraft had entered interstellar space. And technically, that is accurate. Beyond the heliopause, the plasma, the magnetic fields, and the particle environment are dominated by the galaxy rather than by the sun. The Voyagers were swimming in a new ocean. But here is what those headlines did not say clearly enough. Crossing the heliopause is not the same as leaving the solar system, not even close. The sun's gravitational influence extends vastly further than its wind. Gravity does not stop at a boundary. It weakens with distance, but it never truly disappears. And the sun holds objects in orbit at distances so extreme that the heliosphere looks like a puddle by comparison. The Oort cloud is a theoretical shell of icy bodies believed to surround the solar system at distances ranging from roughly 2,000 astronomical units to as far as 100,000 astronomical units from the Sun. Some estimates place the outer edge even further, at perhaps 200,000 astronomical units. To give that number scale, 1 light-year is approximately 63,000 astronomical units. The nearest star, Proxima Centauri, is about 4.24 light-years away, or roughly 268,000 astronomical units. The outer edge of the Oort cloud may reach more than a third of the way to that star. This means that when Voyager 1 crossed the heliopause, it had traveled about 122 astronomical units. The outer edge of the Oort cloud is at least 100,000 astronomical units away. Voyager had completed roughly 0.1% of the journey to the true edge of the solar system's gravitational domain. 0.1%. After 35 years of continuous travel at 38,000 miles per hour. At its current speed, Voyager 1 would need tens of thousands of years to clear the Oort cloud, possibly longer, depending on which estimate of the cloud's outer boundary proves correct. And during every single one of those years, it will still be gravitationally bound to the Sun, still inside the solar system by any rigorous definition. Still falling, in the most technical sense, around a star that has become too faint to see. This is the first and most fundamental deception of the comfortable picture. People imagine leaving the solar system as a dramatic crossing, a single moment where you break free. In reality, it is a process so gradual and so extended that no human being alive today would survive to see it completed, even on the fastest spacecraft ever built. Now, let us talk about what the heliosphere actually does, because its loss is not symbolic, it is operational. The heliosphere is not just a scientific curiosity or a nice label on a diagram. It is a shield. The sun's outward flowing wind and magnetic field create a physical barrier that deflects a significant portion of the galactic cosmic rays, high-energy particles that originate from violent events elsewhere in the Milky Way. Supernovae, neutron-star collisions, and the energetic environments around other stars produce streams of protons and heavier atomic nuclei that travel at nearly the speed of light. These particles carry enough energy to penetrate spacecraft hulls, damage electronic circuits, break strands of DNA, and over time degrade nearly any material exposed to them. Inside the heliosphere, the Sun's magnetic field bends and scatters many of these particles before they can reach the inner solar system. The protection is not absolute. Cosmic rays do reach Earth, but the heliosphere reduces their intensity by a measurable margin. When Voyager 1 crossed the heliopause, its instruments recorded a sharp increase in galactic cosmic ray intensity. The readings confirmed what models had predicted. Outside the bubble, the radiation environment is significantly harsher. NASA's Interstellar Mapping and Acceleration Probe, IMAP, launched in September 2025 and reached its operating position at the Sun-Earth Lagrange Point 1 in January 2026. One of IMAP's primary goals is to map the heliosphere's boundaries in unprecedented detail, precisely because understanding this boundary is critical to understanding the radiation environment that any future deep space mission would face. The mission's instruments are 30 times more sensitive than those on its predecessor, the Interstellar Boundary Explorer. The reason NASA invested in this capability is not academic curiosity. It is because the heliosphere's shape, thickness, and variability directly determine how much galactic radiation penetrates the solar system and how much more a spacecraft would face once it leaves. The point is worth sitting with for a moment. The Sun is not just providing light and warmth, it is actively defending everything inside its influence from the harsher radiation of the galaxy. And the moment you leave that influence, the defense drops away. Not partially, not gradually, in a way that gives you time to adjust. It drops away in a physically measurable step at the heliopause. And from that point forward, you are exposed to the full, unfiltered cosmic ray environment of the Milky Way. This is not the kind of danger that arrives with a warning alarm. It is the kind that accumulates in silence, particle by particle, hour by hour, year by year, and it does not stop. Now, consider the Voyager probes themselves. Because they are the only objects humanity has ever placed beyond the heliosphere, and their story tells you almost everything you need to know about what deep space does to a machine. Voyager 1 and Voyager 2 launched in 1977. They were built to last 5 years. They have now been operating for nearly 48. That is an engineering miracle by any standard. But the miracle is not free. It has a cost, and that cost is being paid in real time, right now, in ways that perfectly illustrate the dangers waiting beyond the solar system. Both Voyagers are powered by radioisotope thermoelectric generators, devices that convert the heat of decaying plutonium-238 into electricity. It is an elegant system designed to provide power for decades without refueling. And it is dying. Each Voyager loses a small but irreplaceable amount of electrical power every year as the plutonium decays. At launch, each spacecraft's generators produced about 470 watts. As of 2026, that number has dropped to roughly 220 watts. That is less than the power needed to run a standard household light bulb. The consequence is brutal and direct. NASA has been shutting down instruments one by one for years. In February 2025, engineers turned off Voyager 1's cosmic ray subsystem. In March, Voyager 2's low-energy charged particle instrument followed. As of now, only 3 science instruments remain active on each spacecraft. Additional shutdowns are scheduled for 2026. The mission team hopes to keep at least one instrument running on each probe into the early 2030s, but they have been explicit that unforeseen problems could end the mission at any time. Think about what that means. The farthest human-made objects in existence are not being brought down by a collision, not by an alien encounter, not by some dramatic space event. They are being slowly starved of the energy they need to function. The plutonium does not care about human ambition. It decays at its own rate, indifferent to whether anyone is listening on the other end. And there is no way to refuel them, no way to swap out the generators, no way to send a repair crew to a spacecraft more than 15 billion miles from Earth. This is what deep space does. It does not kill quickly. It does not announce itself. It simply waits while the systems you depend on quietly degrade, and there is no one to call for help. There is another detail about the Voyagers that most people overlook, and it is one of the most telling. Communication. Voyager 1's radio transmitter operates at roughly 23 watts. That is less power than a refrigerator light bulb. The signal it sends toward Earth spreads out as it travels, weakening with the square of the distance. By the time it reaches Earth, it is so faint that NASA must use its largest deep space network antennas, dishes 70 meters across, just to detect it. The data rate has been reduced to a trickle. What once sent back stunning images of Jupiter and Saturn now transmits a thin stream of numbers so sparse that transmitting a single photograph back to Earth would take weeks, and the delay. As of 2026, a signal from Voyager 1 takes more than 23 hours to reach Earth. Voyager 1 is projected to reach a distance of 1 light day from Earth in November 2026. At that point, a round-trip communication will take 48 hours. If something goes wrong during those 2 days, the spacecraft is on its own. Its onboard computers, built with 1970s technology, must recognize the problem and protect themselves without help from the ground. If a critical system fails in a way the onboard software cannot handle, the mission is over. No second chance, just silence. Here is what makes this relevant beyond the Voyager story. Voyager 1 is roughly 173 astronomical units from the Sun. It has not even begun to enter the Oort cloud. It has not left the solar system. And already, the challenges of distance have pushed the mission to its operational limits. Power is fading. Communication is a whisper. Instruments are shutting down. The spacecraft can no longer be meaningfully controlled in real time. Every decision made on Earth arrives a day late. Now, extend that reality outward. Not to 173 astronomical units, but to 1,000, to 10,000, to 100,000, the distances where the Oort cloud ends and true interstellar space begins. At 10,000 astronomical units, a radio signal traveling at the speed of light would take roughly 2 months to reach Earth. At 100,000 astronomical units, it would take more than a year and a half. A round-trip communication at the outer edge of the solar system would take over 3 years. 3 years to say hello and hear the answer. At those distances, the concept of mission control becomes meaningless. You are not controlling anything. You are sending messages into the void and hoping the machine on the other end is still alive when the message arrives. There is no support, no guidance, no intervention. Whatever is out there is alone in every sense of the word, and the energy problem does not improve with distance. It gets catastrophically worse. Sunlight, which powers virtually all human activity in the inner solar system, follows the inverse square law. At Earth's distance, the Sun delivers roughly 1,360 watts of energy per square meter. At Jupiter's distance, 5 times further from the Sun, that number drops to about 50 watts per square meter. At Neptune, 30 times further, it is roughly 1.5 watts. At the heliopause, 120 astronomical units from the Sun, Solar energy is so faint that even the largest solar panels ever built could not extract enough power to run a household toaster. Beyond the heliopause, solar power is effectively zero for any practical purpose. A mission operating out there must carry its own energy. Radioisotope generators are the only proven technology for this, and as the Voyagers demonstrate, they decay with time. They cannot be recharged. They cannot be replenished. The clock starts the moment they are manufactured, and it does not stop until the plutonium has decayed past the point of usefulness. For a mission that lasts decades, this is manageable with careful planning. For a mission that lasts centuries or millennia, which is what crossing the Oort cloud requires at any speed we can currently achieve, it is a death sentence written in physics. The power runs out. The instruments go dark. The heaters fail. The electronics freeze. And the spacecraft becomes a piece of metal drifting through the dark, indistinguishable from the debris it passes. This is the part of the story that the comfortable picture leaves out. The popular imagination treats leaving the solar system like leaving a harbor. You untie the ropes, raise the sails, and head for open water. The ocean is dangerous, sure, but the ship is the ship. It works the same way whether you are 1 mile from shore or 1,000. Space does not work like that. In space, the harbor is not just a place you leave. The harbor is the reason everything works. The sun provides your energy. Earth provides your communication, your navigation corrections, your repair capability, your emergency support, your psychological connection to everything that makes a mission survivable. Every mile you travel away from the harbor, you lose a fraction of those things. And at some point, you cross a threshold where the losses become total. That threshold is not a wall. It is not marked. There is no sign in space that reads, "Beyond this point, you are on your own." It is a gradient, a slow curve that bends downward so gently that you might not notice the change from one day to the next. But zoom out, look at the full arc, and the curve is unmistakable. It goes to zero. Everything goes to zero. Power, communication, support, rescue, recovery, all of it. And the distance over which that curve flattens to nothing is not the distance to Mars. It is not the distance to Pluto. It is not even the distance to the heliopause. It is the distance to the edge of a region so vast that light itself needs more than a year to cross it. That is what leaving the solar system actually means. Not a dramatic moment of departure. A slow, irreversible descent into a condition where every system you depend on weakens, every connection to safety thins, and every option for recovery quietly disappears. Not because of one catastrophic event, because of the most fundamental force in the universe, distance. And what makes it truly dangerous is what comes next. Because losing the sun's energy and Earth's support is only half the equation. The other half is what you are walking into. The environment beyond the heliosphere is not simply empty. It is actively, measurably, relentlessly hostile in ways that most people have never been told about. And the deeper you go, the worse it gets. There is a concept in engineering that does not get discussed often enough outside of mission planning rooms. It is called the support architecture. Every machine that has ever operated in space, from the earliest satellites to the International Space Station, exists inside an invisible web of systems that keep it alive. Communication links, ground-based navigation corrections, power sources, thermal management, software updates, contingency procedures rehearsed by teams on Earth who can intervene within minutes or hours if something goes wrong. That web is the reason space missions work, not the spacecraft alone. The spacecraft plus every system on Earth that watches it, guides it, corrects it, and rescues it when things go sideways. What most people do not realize is that this architecture has a range. It does not extend forever. It was never designed to. Every component of the support web weakens with distance, and each one weakens at a different rate, following different physical laws, hitting different failure thresholds at different points along the journey outward from the Sun. The result is not a single wall where everything stops working. It is a cascading collapse, one system after another dropping below functional thresholds as the mission moves farther from Earth. And the terrifying part is how early that cascade begins. Let us start with the one that kills most quietly. Power. Every spacecraft needs electricity. Without it, nothing works. Instruments go blind. Computers stop processing. Heaters shut off. Antennas cannot transmit. Valves cannot open or close. The spacecraft becomes an inert object, a piece of debris shaped like a machine, but functionally identical to a rock. In the inner solar system, spacecraft draw their power from the Sun. Solar panels convert sunlight into electricity with an efficiency that has improved over decades of refinement. Modern panels can extract meaningful energy from sunlight as far out as Jupiter's orbit, roughly 5 astronomical units from the Sun. NASA's Juno spacecraft, orbiting Jupiter since 2016, operates on solar power using 3 large panel arrays with a combined wingspan of more than 66 feet. It works, but barely. At Jupiter's distance, the Sun delivers only about 4% of the energy it provides at Earth's distance. Juno's panels generate roughly 500 watts. Enough to operate, but a dramatic reduction from what the same panels would produce closer to the Sun. Beyond Jupiter, solar power becomes impractical. At Saturn's distance, roughly 10 astronomical units, the available sunlight is barely 1% of what Earth receives. At Uranus, about 20 astronomical units, it drops below 1/4%. At Neptune, 30 astronomical units, it is negligible. No solar panel technology that currently exists or is projected to exist within the next several decades can extract useful energy at those distances. The Sun is still visible. You could still see it with your eyes. But as a power source, it is functionally dead. This is why every mission beyond Jupiter's orbit has relied on nuclear power. Specifically, radioisotope thermoelectric generators, the same technology that powers the Voyager probes. These generators work on a simple principle. Plutonium-238 decays naturally, releasing heat. Thermoelectric couples, devices made of 2 different metals, convert that heat difference into a small electrical current. No moving parts. No combustion, no fuel that gets consumed in bursts. Just the slow, predictable release of energy from atoms that are falling apart. The elegance of this system is matched by its cruelty. Plutonium-238 has a half-life of approximately 87.7 years. That means every 87.7 years, half the remaining plutonium has decayed into other elements that produce less usable heat. The power output does not drop suddenly. It declines in a smooth, relentless curve, roughly 4 watts per year for a Voyager-class generator. You cannot stop it, you cannot slow it, you cannot reverse it. From the moment the plutonium is encapsulated and the generator is assembled, the countdown begins. For a mission lasting a decade or 2, this is manageable. The New Horizons spacecraft, which flew past Pluto in 2015, carries a single radioisotope thermoelectric generator that produced approximately 240 watts at launch. By the time it reached Pluto, 9.5 years later, the output had declined to roughly 208 watts, a reduction, but not a crisis. The spacecraft had been designed with that decline in mind. Every instrument, every heater, every communication cycle was budgeted against a power curve that the engineers knew in advance. But stretch the timeline further, much further. A mission to the heliopause takes decades. A mission through the Oort cloud, if such a thing were ever attempted, would take centuries or millennia at any speed achievable with current or near-future propulsion. Over those timescales, the radioisotope generator does not just weaken, it dies. After 3 half-lives, roughly 263 years, the plutonium retains only 12.5% of its original thermal output. After 5 half-lives, roughly 438 years, it retains just over 3%. The generator becomes unable to power even a single instrument. The spacecraft goes cold. The electronics freeze. And somewhere in the dark between stars, a machine that once represented the peak of human engineering becomes silent metal. There is no alternative power source currently available for interstellar distances. Fusion reactors, if they are ever developed for spacecraft, could theoretically provide sustained power for much longer durations, but no working fusion, propulsion, or power system has been demonstrated in space as of 2026. Beamed power, where energy is transmitted to a spacecraft from a large laser or microwave station near the Sun, has been proposed for concepts like breakthrough starshot, but this approach works only for very small, lightweight probes, and only during the initial acceleration phase. Once the beam can no longer reach the spacecraft, or the probe moves beyond the beam's effective range, the craft is on its own. The power problem is not a detail that can be engineered around with clever design. It is a physical limit imposed by the nature of radioactive decay and the absence of any alternative energy source in interstellar space. Distance does not just make power harder to generate. Beyond a certain range, it makes sustained power generation impossible with any technology that exists. Now, layer on the second collapse. Communication. Radio waves travel at the speed of light. That is fast. Roughly 186,000 miles per second. Nothing in the universe moves faster. And yet, the speed of light is grotesquely slow compared to the distances involved in leaving the solar system. At Mars, depending on orbital positions, a radio signal takes between 3 and 22 minutes to reach Earth. That delay is manageable. Rover operators send a command, wait for confirmation, and adjust. But even at Mars, real-time control is impossible. Every action was decided minutes ago. Every response arrives minutes late. Push the distance outward, and the delay compounds relentlessly. At Jupiter, the one-way delay reaches nearly an hour. At the heliopause, roughly 17 hours. At Voyager 1's current distance, more than 23 hours, Voyager 1 is projected to reach a distance of 1 light day from Earth in November 2026. At that point, a one-way signal will take 24 hours to arrive. A round-trip communication, send a command and receive a response, will take 2 full days. If an anomaly occurs on Monday morning, mission controllers will not know about it until Tuesday morning. Their corrective command will not arrive at the spacecraft until Wednesday morning. And confirmation that the fix worked will not reach Earth until Thursday morning. 4 days to close a single loop of communication. For a spacecraft that is still, by interstellar standards, right next door, at the inner edge of the Oort cloud, roughly 2,000 astronomical units from the Sun, a one-way signal would take approximately 11.5 days. A round trip would take 23 days. At the outer edge, 100,000 astronomical units, a one-way signal would take approximately 1.5 years. A round trip would take 3 years. 3 years to ask a question and hear the answer, but the delay is only half the communication problem. The other half is signal strength. Radio signals do not travel as tight beams forever. They spread out. The power of a radio signal decreases with the square of the distance from the transmitter. Double the distance, and the signal arriving at the receiver is 4 times weaker. Triple the distance, 9 times weaker. Increase the distance by a factor of 10, the signal drops to 1/100th of its original strength. That 23-watt signal, after traveling more than 15 billion miles, has spread across an area so vast that the power intercepted by NASA's 70-meter deep space network dishes is on the order of 10 to the -16th watts. That is a decimal point, followed by 15 zeros and then a 1. It is a quantity so small that detecting it requires cooling the receiving equipment to near absolute zero to reduce electronic noise, then running the faint signal through layers of amplification and error correction software, and this is at 173 astronomical units. The technology works, the signal is detected, but the system is operating at the extreme edge of its capability. The data rate from Voyager 1 has been reduced to approximately 160 bits per second. That is roughly 1/6000th the speed of a basic household internet connection. Transmitting a single photograph at that rate would take weeks. At 10 times the distance, the signal would be 100 times weaker. At 100 times the distance, 10,000 times weaker. At the outer edge of the Oort cloud, the signal from a Voyager-class transmitter would be so faint that no antenna on Earth, no antenna that could feasibly be built on Earth, would be capable of detecting it. The spacecraft would still be transmitting. The radio waves would still be spreading outward at the speed of light. But the whisper would be too quiet for anyone to hear, and the physics of signal decay is only half of the communication problem. The other half is the infrastructure on the ground. Because even within the distances where signals can theoretically be detected, humanity's ability to listen depends on a system so small, so overcommitted, and so fragile that most people would be alarmed if they understood how thin it actually is. The Deep Space Network is the only system on Earth capable of communicating with spacecraft beyond the Moon. It consists of 3 facilities, spaced roughly 120 degrees apart around the globe, one near Canberra in Australia, one near Madrid in Spain, and one near Goldstone in California. The spacing ensures that at least one facility has line of sight to any point in the sky at any time, so that communication with distant spacecraft is never interrupted by Earth's rotation, and the network does not exist solely for the Voyagers. It supports every active deep space mission simultaneously, from Mars rovers to solar probes to IMAP, along with missions from the European Space Agency, the Japan Aerospace Exploration Agency, and other international partners. Scheduling is a constant negotiation. Antenna hours are allocated based on mission criticality and data urgency, and as the number of active missions has grown over the past 2 decades, demand has consistently outpaced supply. The fundamental bottleneck remains. There are only a handful of antennas on Earth large enough to communicate with spacecraft at extreme distances, and every new mission adds to the queue. This matters for the Voyagers right now. Both spacecraft are so far from Earth that only the largest dishes can detect their signals. And as we discussed, when Deep Space Station 43 was taken offline for upgrades between May 2025 and February 2026, the Voyager team had only narrow windows to send commands. If either spacecraft had experienced a critical anomaly outside those windows, the team would have been unable to respond. During that period, the Voyager team had only narrow windows in August and December to send commands. If either spacecraft had experienced a critical anomaly outside those windows, the team would have been unable to respond. The mission's survival depended entirely on the spacecraft's own ability to protect themselves. Now project this constraint outward. A spacecraft at 1,000 astronomical units would require an antenna sensitivity orders of magnitude beyond what the Deep Space Network currently provides. At 10,000 astronomical units, the requirements move into a regime that no ground-based facility on Earth could achieve without a fundamental redesign of how we build and operate radio telescopes. And no such redesign is currently funded, planned, or even in the conceptual pipeline at any space agency on Earth. The communication collapse is not just a problem of physics, it is a problem of infrastructure. The system humanity, built to talk to its spacecraft, was designed for the solar system. It was sized for the solar system. It was funded for the solar system. And it is already straining under the demands of the solar system. The idea that this same system could support a mission to interstellar space is not optimistic. It is disconnected from the reality of how the system actually works, what it actually costs, and how close it already is to its operational limits. This means that beyond a certain distance, communication with a spacecraft does not just slow down, it ceases. The link between the machine and the people who built it is severed. Not by a dramatic event, not by a malfunction, by physics. The inverse square law does not care about human ingenuity. It applies equally to every signal, every frequency, every transmitter. And at interstellar distances, it wins. Now, add the third collapse. Navigation. Navigating in deep space is not like navigating on Earth. There are no landmarks, no roads, no GPS constellation. Determining where a spacecraft is and where it is heading requires a combination of techniques, all of which rely on the connection between the spacecraft and Earth. The primary method is called radiometric tracking. Ground stations send a precisely timed signal to the spacecraft, which returns it. By measuring the round-trip travel time and Doppler shift, engineers calculate distance and velocity with extraordinary precision. This system has guided every deep space mission NASA has ever flown, but it depends entirely on the communication link. If the signal is too weak to detect, radiometric tracking fails. If the delay is too long, the position data represents where the spacecraft was days or months ago, not where it is now. Onboard star trackers can determine which direction the spacecraft is pointing, but they cannot determine where it is in space. No autonomous position determination system exists for interstellar distances. The Deep Space Network, NASA's array of large dish antennas spread across 3 sites in California, Spain, and Australia, is the backbone of every deep space communication and navigation effort. It is a marvel of engineering. But it was designed for missions within the solar system. Its dishes, even the 70-meter giants, have physical limits on how faint a signal they can detect and how far they can track a spacecraft with useful precision. And here is a detail that illustrates how thin the margins already are. Deep Space Station 43, the 70-meter antenna at the Canberra facility in Australia, is the only antenna in the entire network that can send commands to the Voyager spacecraft. Between May 2025 and February 2026, that antenna was taken offline for major upgrades, with only limited operational windows in August and December 2025. During that period, if either Voyager encountered a serious anomaly, the ability to send corrective commands was severely constrained. The mission's survival depended on the spacecraft's own ability to recognize problems and protect themselves without human intervention. That is the reality of deep space navigation and communication today. It works, but it works at the edge. And every additional astronomical unit of distance pushes it closer to the point where it does not work at all. Now, add the fourth collapse. Repair. In low Earth orbit, where the International Space Station operates, repair is difficult but possible. Astronauts can conduct spacewalks. Resupply missions arrive regularly. Replacement parts can be launched from the surface within weeks or months. The station is roughly 250 miles from Earth. Help is close. At the Moon, roughly 240,000 miles away, repair becomes harder. Response times are longer. Resupply is more expensive. But it is still physically achievable. NASA's Artemis program is designed around the assumption that crews operating at the Moon can be supported from Earth with reasonable turnaround times. At Mars, roughly 140 million miles away, at its closest approach, repair from Earth becomes a serious challenge. A resupply mission would take months to arrive. An emergency evacuation is essentially impossible with current technology. Mars crews will need to be largely self-sufficient, carrying spare parts, tools, and the knowledge to fix things themselves. This is already a fundamental change in the nature of space missions. But at least at Mars, the communication delay is manageable. A crew can consult with engineers on Earth and receive guidance within an hour. Beyond Mars, the concept of repair from Earth begins to dissolve entirely. At Jupiter's distance, a replacement part launched from Earth would take years to arrive, assuming anyone could even launch a targeted resupply mission to a moving spacecraft billions of miles away. At Saturn's distance, the transit time is even longer. At the heliopause, the idea is absurd. No resupply ship exists that could reach a spacecraft 120 astronomical units from Earth within any useful time frame. And in interstellar space, the concept is not just impractical, it is meaningless. A spacecraft traveling through the Oort cloud is on its own in the most absolute sense that phrase has ever carried. If a circuit fails, it stays failed. If a fuel line freezes, it stays frozen. If a micrometeoroid punches a hole in a critical system, the hole remains. There is no one to call. There is no one coming. The spacecraft must either fix itself or accept the damage. The Voyager probes have confronted this reality repeatedly. In 2024, Voyager 1 experienced a malfunction in its flight data subsystem that caused it to send garbled data back to Earth instead of readable science and engineering information. The team at the Jet Propulsion Laboratory spent months diagnosing the problem from 15 billion miles away, eventually determining that a single malfunctioning chip in the spacecraft's memory was corrupting the data. They devised a workaround, redistributing the affected code across other sections of the computer's memory, and transmitted the fix to the spacecraft. The repair took roughly 5 months from detection to resolution. 5 months to fix a software problem on a spacecraft that is still within communication range. Imagine the same failure occurring on a probe deep in the Oort cloud, where a round-trip signal takes months or years instead of 2 days. The diagnosis alone could take years. The fix, if one exists, could arrive after the spacecraft has already deteriorated past the point of recovery. Now, consider what this means for any crewed mission. A human crew traveling beyond the heliopause would carry their ship, their air, their water, their food, their medical supplies, and their own expertise. Everything they will ever need for the duration of the mission must be on board at departure or manufactured from resources gathered along the way. There are no resources to gather in interstellar space. No asteroids to mine between the Oort cloud and the nearest star. No water ice to melt. No minerals to process. The space between stars is not empty in the strictest physical sense. There are roughly 1 or 2 atoms of hydrogen per cubic centimeter. But it is empty in every sense that matters for survival. You cannot build anything from 1 atom per cubic centimeter. You cannot breathe it. You cannot drink it. You cannot use it to patch a hull breach or replace a failed component. A crewed mission to interstellar space would need to be entirely self-contained for the full duration of the voyage, decades at a minimum, centuries more realistically. Every tool, every spare part, every gram of medicine, every calorie of food would need to be accounted for before launch. And the margin for error would be essentially zero, because there is no backup, there is no rescue ship, there is no emergency landing site. There is no friendly port where you can stop and resupply. The fifth collapse ties all the others together. Redundancy. In engineering, redundancy means having backup systems. If one computer fails, a second takes over. If one thruster clogs, another fires instead. If one antenna breaks, a spare can be deployed. Redundancy is the reason spacecraft survive in hostile environments. It is the margin between a mission that recovers from a problem and a mission that dies from one. But redundancy has limits. Every backup system adds weight. Every spare component requires power. Every additional piece of hardware increases the complexity of the spacecraft and the number of things that can fail. Engineers must balance the desire for redundancy against the constraints of mass, power, and volume. And for missions of extreme duration, the balance becomes impossible to maintain. Consider a spacecraft designed to operate for 50 years. It needs 50 years of consumables, 50 years of spare parts for every critical system, 50 years of fuel for attitude control, 50 years of power decline factored into every operational decision. The mass budget for such a mission is staggering. And mass is the fundamental constraint of spaceflight. Every kilogram you add to the spacecraft requires more fuel to accelerate, which adds more mass, which requires more fuel. The relationship is exponential. It is governed by the rocket equation, one of the most unforgiving formulas in all of physics. For a mission lasting 500 years, the mass budget is not just staggering. It is physically unachievable with any propulsion technology that exists or is currently projected. You cannot carry enough spare parts to maintain a spacecraft for 5 centuries. You cannot carry enough fuel to make corrections over that duration. You cannot carry enough shielding to protect against 500 years of cosmic ray exposure. The numbers do not close. The margins do not exist. And there is one more dimension to the navigation and survival problem that rarely appears in popular discussions of interstellar travel. The Oort cloud is not just a distance marker. It is a place. And what fills that place makes the journey through it a navigational hazard in its own right. The Oort cloud is a theoretical structure, never directly observed but strongly inferred from the orbits of long-period comets that fall toward the inner solar system from every direction. These comets arrive on trajectories that suggest they originate from a vast, roughly spherical shell of icy bodies surrounding the Sun, at distances ranging from about 2,000 to as far as 100,000 astronomical units. The number of objects in the Oort cloud is estimated to be in the hundreds of billions, possibly exceeding 1 trillion. Their combined mass is uncertain, but may be several times the mass of Earth. These are not dust grains. The objects in the Oort cloud are substantial bodies. Cometary nuclei, the cores of the objects that occasionally fall into the inner solar system and develop tails as they approach the Sun, range in size from a few hundred meters to tens of kilometers across. The Oort cloud is believed to contain a full spectrum of sizes, from pebbles to objects potentially rivaling dwarf planets in diameter, all orbiting the Sun at immense distances in near total darkness. Near total darkness is the critical phrase. At 2,000 astronomical units from the Sun, sunlight is roughly 4 million times dimmer than it is at Earth's distance. At 50,000 astronomical units, it is 2.5 billion times dimmer. These objects do not glow. They do not reflect enough light to be detected by any telescope on Earth or any sensor aboard a spacecraft. A spacecraft transiting the Oort cloud at Voyager speeds roughly 17 kilometers per second, would have no ability to detect an Oort cloud body in its path. The spacecraft would not know an object was there until the moment of impact. And at 17 kilometers per second, the moment of impact is also the moment the mission ends. The probability of a direct collision with any single Oort cloud body during a transit is extremely low. The Oort cloud is vast, and even trillions of objects spread across a shell that extends to 100,000 astronomical units occupy an almost negligibly small fraction of the total volume. The average spacing between objects may be billions of kilometers. A spacecraft threading through this region has an overwhelming statistical likelihood of passing through without striking anything. But the transit takes 30,000 years. And over 30,000 years, even a very small annual probability accumulates. The math of compounding risk applies to Oort cloud collisions just as it applies to micrometeoroid impacts and electronic failures. A 1 in a million chance per year becomes a meaningful, cumulative probability over tens of thousands of years. A 1 in 100,000 chance per year becomes a 26% chance. The numbers depend on assumptions about the density distribution and size distribution of Oort cloud objects. And those assumptions carry significant uncertainty because the Oort cloud has never been directly observed. What is certain is that the hazard is real, it is undetectable with any technology that currently exists, and it persists for the entire duration of the transit. A spacecraft crossing the Oort cloud is flying blind through a sparse but real minefield for thousands of years, with no ability to see, avoid, or survive a collision with any object larger than a grain of sand. This is distinct from the micrometeoroid hazard of the interstellar medium, which involves dust grains measured in micrometers impacting at high velocities. The Oort cloud hazard involves macroscopic objects, bodies large enough to annihilate a spacecraft on contact in a region where detection is impossible and evasion is meaningless. It is a risk that cannot be mitigated by shielding, because no shield can protect against an impact with a body the size of a house. It can only be accepted as a probability, a slow roll of dice repeated every year for 30 millennia. This is the architecture of support. And this is how it collapses. Not all at once. Not in a single dramatic failure. One system at a time. Power weakens. Communication fades. Navigation loses precision. Repair becomes impossible. Redundancy is exhausted. Each collapse makes the next more likely, because a spacecraft with less power has less ability to communicate, which means less ability to receive navigation corrections, which means less ability to identify and fix problems before they cascade into mission-ending failures. And all of this happens not because of any hostile force, not because something attacks the spacecraft, not because of a design flaw or a human error. It happens because of distance, pure, simple, undefeatable distance. The kind of distance that does not fight you. It just waits while everything you brought with you slowly runs out. The uncomfortable truth is that every space mission humanity has ever flown has operated inside a safety net woven from the sun's energy and Earth's proximity. We have never operated without that net. Not truly. Even the Voyagers, humanity's boldest reach into the void, were designed as instruments, not as vessels for survival. They carry no crew. They have no need for life support. They are small, simple, and expendable. And even they are being brought to their knees by the physics of distance. A crewed mission to interstellar space would face every one of these collapses, plus an entirely new category of dangers that machines do not experience. Biological dangers, psychological dangers. The dangers that come from putting living, breathing, thinking human beings into a condition that no human being was ever built to endure. A condition defined not by violence, but by silence, darkness, cold, and the knowledge that no one is coming to help. Those dangers are the subject of what comes next. Because the collapse of Earth's support is only one side of the equation, the other side is what the environment beyond the heliosphere actively does to anything that enters it. And that environment is not the peaceful, empty void that most people imagine. It is a slow-burning furnace of radiation, a gauntlet of microscopic projectiles, and a thermal wasteland that conspires to destroy every material, every circuit, and every living cell that dares to cross into it without the sun's protection. There is a temptation to think of interstellar space as empty. The word void gets used so often in descriptions of deep space that it has become almost synonymous with the region between stars, and in one narrow sense, it is accurate. Roughly 1 atom per cubic centimeter on average across the galaxy, and somewhat less in the local region near the solar system, compared to the 25 quintillion molecules per cubic centimeter in the air around you right now. A vacuum so thorough it barely qualifies as existing. But calling it empty is a mistake, a dangerous one, because the interstellar medium is not defined by what it lacks, it is defined by what it carries. And what it carries, in terms of energy, radiation, and high-velocity particles, is enough to kill a human being, destroy a spacecraft's electronics, and degrade any known material over the timescales required to cross it. The heliosphere, the sun's protective magnetic bubble, is the reason this distinction matters. Inside the heliosphere, the solar wind and its embedded magnetic field actively push back against the most dangerous component of the interstellar environment: galactic cosmic rays. These are not the gentle waves of light that warm your skin on a summer afternoon. They are atomic nuclei, mostly protons but also heavier elements like helium, carbon, oxygen, and iron, stripped of their electrons and accelerated to velocities approaching the speed of light. Their energies are extraordinary. The most energetic cosmic rays ever detected carry as much kinetic energy as a professionally pitched baseball, compressed into a single subatomic particle. Even the far more common lower-energy cosmic rays carry enough force to disrupt molecular bonds and damage electronic circuits with every impact. These particles originate from the most violent events in the galaxy. Supernovae, the explosive deaths of massive stars, are the primary source. When a star 20 times the mass of the Sun exhausts its fuel and collapses, the resulting explosion blasts material outward at a significant fraction of the speed of light. Shock waves from these explosions accelerate particles to extreme energies over thousands of years, creating a persistent background of high-energy radiation that permeates the entire Milky Way. Neutron star mergers, black hole jets, and other energetic phenomena contribute additional particles. The result is a galaxy-wide bath of radiation that fills every cubic centimeter of interstellar space. Inside the heliosphere, the Sun's magnetic field provides partial shielding. The solar wind carries magnetic field lines outward from the Sun, and these lines deflect and scatter many incoming cosmic rays before they can reach the inner solar system. The shielding is not perfect. Cosmic rays do reach Earth. They contribute to background radiation levels on the surface and at altitude. Airline pilots and frequent flyers receive measurably higher radiation doses than people who stay on the ground. Astronauts aboard the International Space Station, which orbits within Earth's magnetosphere but above most of the atmosphere, receive radiation doses roughly 10 times higher than the average person on the surface. But the heliosphere reduces the intensity of galactic cosmic rays by a significant margin. The exact reduction depends on the solar cycle. During periods of high solar activity, when the Sun's magnetic field is strongest and most turbulent, cosmic ray intensity inside the heliosphere drops. During solar minimum, when the field weakens, cosmic ray intensity rises. For the moderate energy cosmic rays that contribute most to biological dose, the heliosphere can reduce intensity by roughly 30 to 50% or more, though the highest energy particles pass through the heliosphere's shielding with little deflection. When Voyager 1 crossed the heliopause in 2012, it measured a dramatic increase in galactic cosmic ray intensity. The readings confirmed what models had predicted for decades. Beyond the heliosphere, the cosmic ray environment is substantially harsher. The protective bubble is gone. The magnetic deflection is gone. Every particle that the heliosphere would have scattered or slowed now arrives with its full energy, from every direction, continuously. For a robotic spacecraft, this is a problem, but not an immediate death sentence. Cosmic rays can cause single-event upsets in electronic circuits, flipping bits in computer memory, corrupting data, and occasionally triggering unintended commands. Spacecraft designed for deep space missions are built with radiation-hardened electronics and error correction software to manage these events. The Voyagers have experienced thousands of single-event upsets over their nearly 5 decades of operation. Most were caught and corrected automatically. A few caused significant anomalies that required intervention from Earth, but the rate of these events increases outside the heliosphere. More cosmic rays mean more interactions with electronic components. More interactions mean more single-event upsets, more accumulated radiation damage to semiconductors, and a higher probability of a multi-bit error that the error correction system cannot handle. Over years and decades, this accumulated dose degrades the performance of every electronic system on the spacecraft. Transistors slow down. Memory cells lose their ability to hold a charge reliably. Sensors drift. The spacecraft ages not just mechanically, but electrically, its brain slowly deteriorating. Under a constant rain of particles, it was never designed to endure indefinitely. For a human crew, the situation is incomparably worse. The human body is not radiation hardened. Every cell in your body contains DNA, and DNA is exquisitely sensitive to ionizing radiation. When a galactic cosmic ray passes through a living cell, it can break chemical bonds in the DNA molecule, snapping the double helix like a bullet through a thread. The cell has repair mechanisms. It can fix many types of damage. But galactic cosmic rays, particularly the heavy ion component known as HZE particles, which stands for high atomic number and high energy, cause a specific type of damage that is exceptionally difficult to repair. When an HZE particle, say an iron nucleus traveling at 90% of the speed of light, passes through a cell, it does not just break a single bond. It creates a track of destruction through the cell, ionizing hundreds of molecules along its path. The damage is clustered, concentrated in a narrow column that overwhelms the cell's repair capacity. The result can be cell death, which in small numbers is manageable. The body replaces dead cells constantly, but it can also be something worse. The cell can survive with damaged DNA, misrepaired or incompletely repaired, and begin to replicate with errors that accumulate over time into cancer. NASA has studied the cancer risk from galactic cosmic rays extensively. In 2022, the agency revised its career dose limit for astronauts to 600 millisieverts of cumulative exposure, applied uniformly regardless of age or sex. For a 6-month mission to the International Space Station, the exposure typically remains within this limit. For a 3-year round-trip mission to Mars, which would involve roughly 18 months of transit through interplanetary space with minimal shielding, the cumulative dose approaches or potentially exceeds this limit depending on the solar cycle and the spacecraft's shielding mass. For a mission beyond the heliosphere, the exposure is in a different category entirely. The cosmic ray intensity is higher, The duration is longer, decades longer, centuries longer, if the mission is actually attempting to reach another star. And the shielding problem is worse than most people realize. Shielding against galactic cosmic rays is not like shielding against other forms of radiation. Lead, which is excellent at stopping X-rays and gamma rays, is actually counterproductive against the highest energy cosmic rays. When a very high energy particle strikes a heavy nucleus like lead, it can undergo a nuclear reaction called spallation, shattering the lead nucleus into a shower of secondary particles, neutrons, protons, and lighter nuclei that spray outward into the spacecraft's interior. The secondary radiation can be more biologically damaging than the original particle. Adding more LED makes the problem worse, not better. The best shielding materials against cosmic rays are light elements. Hydrogen is the most effective per unit mass because its nucleus is a single proton, which minimizes the production of secondary particles during collisions. Water, which contains 2 hydrogen atoms per molecule, is a reasonable shielding material and has the advantage of being useful for other purposes on a crewed mission. Polyethylene, a common plastic rich in hydrogen, has also been studied as shielding material, but even with optimal materials, the mass required to provide meaningful protection against the full spectrum of galactic cosmic rays is enormous. NASA studies have estimated that reducing the cosmic ray dose by 50% on a Mars-class mission would require several tens of centimeters of polyethylene or water surrounding the crew habitat. The mass penalty for this shielding is measured in tens of thousands of kilograms. For a larger habitat designed for a longer mission, the mass increases proportionally. And here is the critical point. Even with the best shielding, you cannot reduce the dose to 0. The highest energy cosmic rays, those with energies above roughly 1 gigaelectronvolt per nucleon, are essentially unstoppable by any passive shielding of practical thickness. They will pass through meters of material without being fully absorbed. A spacecraft crew in interstellar space would receive a continuous, low-level radiation dose for the entire duration of the mission, year after year after year. The cumulative effect over decades is not merely an elevated cancer risk. It includes potential damage to the central nervous system. Research published by NASA's Space Radiation Laboratory has shown that exposure to HZE particles can cause measurable cognitive impairment in animal models. Mice exposed to radiation doses simulating deep space cosmic ray environments showed reduced performance on memory and learning tasks, increased anxiety-like behaviors, and structural changes in the neurons of the hippocampus and prefrontal cortex. The damage appears to involve chronic neuroinflammation triggered by the radiation, a persistent immune response in the brain that degrades neural function over time. These findings are preliminary. Extrapolating from mouse models to human beings involves significant uncertainty. But the direction of the evidence is consistent and concerning. A human crew exposed to unshielded or inadequately shielded cosmic radiation for years or decades could experience progressive cognitive decline, memory loss, reduced decision-making ability, increased anxiety, and impaired emotional regulation. On a mission where the crew must be entirely self-sufficient, where every critical decision depends on their mental acuity, and where no medical evacuation or relief crew is possible, cognitive impairment is not merely a health concern, it is a mission survival concern. But radiation is not the only force working against the body. The human organism evolved under a specific set of physical conditions: gravity, atmosphere, light cycles, immune stimulation from a living biome, the constant presence of other people, and every one of these conditions would be absent or degraded on an interstellar mission. The biological consequences are not speculative. They are documented, measured, and in some cases alarming. Start with gravity, or rather, the lack of it. In microgravity, the human skeleton begins to lose density almost immediately. Without the constant stress of supporting body weight, bone breakdown continues at its normal rate while new bone formation slows. The result is a net loss averaging roughly 1 to 2% per month in weight-bearing bones like the spine, pelvis, and legs. Over a year, an astronaut can lose 10 to 15% of their bone density in these regions. NASA's studies of astronauts who spent a year aboard the International Space Station have confirmed that this loss is partially, but not fully, reversible upon return to Earth. Recovery takes months to years, and some studies suggest that the bone microarchitecture, the fine internal lattice that gives bones their strength, may not fully recover even after extended rehabilitation. For a crew on a multi-decade mission with no prospect of returning to normal gravity, the loss would be cumulative and permanent. After several years, the crew's skeletons would be significantly weakened. Fractures from ordinary movements, bending, lifting, even coughing, would become an increasing risk. Muscle atrophy follows a similar pattern. In microgravity, the large postural muscles of the legs and back, the muscles that work constantly against gravity on Earth, begin to waste within days. Without resistance, the muscle fibers shrink. Strength declines. Cardiovascular fitness deteriorates because the heart, itself a muscle, no longer has to pump blood against a full gravity gradient. Astronauts, returning from 6-month missions, frequently experience orthostatic intolerance, the inability to stand without dizziness or fainting, because their cardiovascular systems have deconditioned. Exercise regimens aboard the station slow the deterioration but do not eliminate it, and the equipment itself requires maintenance, replacement parts, and power that are finite and irreplaceable beyond the solar system. Vision impairment adds another layer. More than half of astronauts who have spent extended time on the International Space Station have experienced changes to their vision, a condition now formally designated spaceflight-associated neuroocular syndrome. The mechanism appears to involve altered fluid distribution in microgravity. Without gravity pulling blood and cerebrospinal fluid downward, pressure in the skull increases, compressing the optic nerve and reshaping the eyeball. Some astronauts have experienced permanent changes to their vision that did not resolve after return to Earth. On a mission lasting decades, the progressive nature of this condition could leave crew members with significantly impaired eyesight, a critical liability when the mission depends on visual monitoring of instruments, manual repairs, and navigation. Immune suppression compounds all of the above. Studies of astronauts have shown measurable immune dysregulation during spaceflight, including reactivation of latent viruses such as varicella zoster and Epstein-Barr. In a closed environment with a small crew, this dysregulation increases the risk of opportunistic infections and reduces the body's ability to fight them. Each of these biological effects is manageable in isolation on a 6-month or even a year-long mission, with the prospect of return to Earth and full medical support. On a multi-decade interstellar mission, they do not exist in isolation. They compound. A crew member with weakened bones, atrophied muscles, impaired vision, a suppressed immune system, and accumulating radiation damage to their DNA is not merely less healthy than they were at departure. They are progressively less capable of performing the physically and mentally demanding tasks that the mission requires for survival. The body that evolved to thrive on Earth begins to fail, slowly and systematically, the moment it leaves the conditions it was built for. And in interstellar space, there is no return to those conditions. The deterioration continues for the duration of the mission, which means for the rest of the crew member's life. There is one more biological dimension that amplifies all of the above, and it is the one that mission planners find most difficult to address: medical self-sufficiency. Every crewed space mission in history has operated within evacuation range of Earth. On the International Space Station, a Soyuz or Crew Dragon capsule is always docked and ready. If an astronaut suffers a heart attack, a burst appendix, a severe allergic reaction, or a traumatic injury, the crew can seal the patient in the capsule and begin a return to Earth within hours. Advanced medical care, surgery, intensive care, specialist consultation is available on the ground within a day of the decision to evacuate. Even on a Mars mission, which would stretch evacuation timelines to months rather than hours, the crew would have the theoretical option of returning to Earth. The transit would be brutal for a critically ill patient, but the option exists. Earth is still reachable. Hospitals still exist at the end of the journey. Beyond the heliosphere, evacuation is a meaningless concept. There is no return within any medically relevant time frame. If a crew member develops a condition that requires surgery, the surgery must be performed on board by crew members who may have received surgical training but who are not practicing surgeons, using equipment that was packed years or decades ago and that may have degraded in storage. If the condition requires a specialist, no specialist is available. If it requires a medication that has expired or been consumed, no replacement exists. Pharmaceuticals degrade. Most oral medications remain effective for 2 to 5 years under proper storage conditions, and no formulation has been validated for the multi-decade durations an interstellar mission would require. A crew that departs with a fully stocked pharmacy will find, after a decade or two, that many of their medications have lost potency or degraded into compounds that may be harmful. On-board pharmaceutical manufacturing, a concept NASA has explored in preliminary studies, could theoretically produce certain drugs from precursor chemicals. But the technology is in its infancy. The range of producible drugs is narrow, and the system itself would require power, maintenance, and expertise that are finite and irreplaceable. Dental emergencies are a particularly mundane but illustrative example. A cracked tooth, an abscess, an impacted wisdom tooth. These are common medical events that affect a significant percentage of the adult population over any multi-year period. On Earth, they are routine problems handled by trained dentists with specialized equipment. On an interstellar spacecraft, they are potential crises. An untreated dental abscess can spread, becoming a systemic infection. A jaw infection in a crew member with a radiation-suppressed immune system could become life-threatening. The treatment requires antibiotics that may have expired, surgical drainage that requires sterile instruments and training, and follow-up care that competes with every other demand on the crew's time and resources. Now multiply this across every category of medical event that a small population will experience over decades. Fractures, especially likely given progressive bone density loss. Kidney stones, which occur at elevated rates in microgravity due to altered calcium metabolism. Cardiac events, increasingly probable as cardiovascular deconditioning advances. Psychiatric emergencies, depression severe enough to impair function, psychotic episodes triggered by stress and isolation, interpersonal violence in a confined population under chronic strain. Each of these requires intervention. Each intervention requires resources. And the resources are finite, degrading, and irreplaceable. The medical reality of an interstellar mission is not a footnote to the engineering challenges. It is a central constraint. A crew that cannot maintain its own health cannot maintain the spacecraft. A crew that loses members to treatable conditions because the treatment was unavailable suffers not just a human tragedy, but a mission capability loss that compounds every other problem. Fewer healthy crew members means fewer people to stand watch, perform repairs, monitor systems, and make decisions. The margin for survival narrows with every illness, every injury, and every death that the mission's medical infrastructure cannot prevent. This is exposure in its most intimate form. Not exposure to radiation or cold or vacuum, but exposure to the ordinary fragility of the human body in a place where the ordinary systems of care and recovery do not exist. The body breaks down. It has always broken down. On Earth, we repair it. In the inner solar system, we can evacuate and repair it. Beyond the solar system, we can only watch it happen and do the best we can with whatever we brought. And cosmic rays are not the only environmental hazard beyond the heliosphere. There is another one that operates on a completely different time scale and through a completely different mechanism. Micrometeoroids. The interstellar medium contains dust, not the kind of dust that settles on your bookshelf. Microscopic grains of silicate, carbon, and ice, ranging in size from fractions of a micrometer to a few micrometers across. These grains are produced by dying stars, supernovae, and the slow erosion of larger bodies over billions of years. They are sparse. The density of interstellar dust is extraordinarily low by terrestrial standards, but they are there. And the spacecraft is moving through them. The danger of a micrometeoroid impact is not about the mass of the particle, it is about the relative velocity. A dust grain weighing less than a millionth of a gram is harmless if it is sitting still. But a spacecraft traveling at even a modest fraction of the speed of light, or even at the roughly 17 kilometers per second that the Voyager probes move, encounters these grains at velocities where the kinetic energy transforms a speck of dust into a weapon. Kinetic energy scales with the square of velocity, double the speed, and the energy of impact quadruples. At 17 kilometers per second, a grain of dust, 1/10 of a millimeter across, carries enough energy to excavate a crater in metal many times its own diameter. At 1% of the speed of light, roughly 3,000 kilometers per second, the same grain carries enough energy to punch through centimeters of spacecraft hull material. At 10% of the speed of light, the energy per particle reaches levels comparable to small explosive charges. For the Voyager probes, moving at roughly 17 kilometers per second through a region of relatively low dust density, micrometeoroid impacts are a chronic low-level risk rather than an acute threat. The spacecraft structure provides some inherent shielding, and the probability of a mission-ending impact in any given year is small, but it is not zero. And over 30,000 years, the time required for Voyager to traverse the Oort cloud, even a very small annual probability, compounds into near certainty. For a faster spacecraft, one designed to reach another star within a human lifetime, the problem becomes dramatically worse. Even proposed interstellar mission concepts that envision accelerating probes to a significant fraction of the speed of light face this problem in its most extreme form. At those velocities, even an atom of hydrogen in the interstellar medium becomes a source of damaging radiation upon impact. A grain of dust, 1 micrometer across, would strike with the energy of a small bullet. The faster you go, the more lethal the dust becomes. Shielding against micrometeoroid impacts at interstellar velocities is an unsolved engineering problem. Traditional meteoroid shielding, like the Whipple shields used on the International Space Station, works by placing a sacrificial bumper layer in front of the main hull. When a particle strikes the bumper, both the impactor and the bumper material fragment into a cloud of smaller debris that spreads its energy across a wider area of the rear wall, preventing a single focused penetration. These shields are effective against particles traveling at a few kilometers per second. At hundreds or thousands of kilometers per second, impact energies are so high that both shield and impactor vaporize into plasma that can damage the structure behind it. The longer the mission, the higher the cumulative probability of a damaging impact. A 20-year mission at 10% of the speed of light faces a dust environment that delivers thousands of times more kinetic energy per unit area than a 20-year mission at Voyager speeds. And every impact that does not destroy the spacecraft still degrades it. Surface erosion, optical coating damage, antenna pitting, thermal blanket degradation. Each impact makes the spacecraft slightly less capable. Over decades, the cumulative erosion adds up to a measurable reduction in performance. Now consider the thermal environment. Space is commonly described as cold. And it is, in the sense that the cosmic microwave background radiation, the remnant heat from the Big Bang, corresponds to a temperature of approximately 2.7 Kelvin. That is roughly minus 455 degrees Fahrenheit. But temperature in space is a more complicated concept than it appears. In the inner solar system, a spacecraft's temperature is primarily determined by its orientation relative to the Sun. The sunlit side absorbs solar radiation and heats up. The shaded side radiates heat into space and cools down. Thermal engineers carefully design spacecraft surfaces using reflective coatings, insulating blankets, and heater systems to keep the interior within the narrow temperature range that electronics and instruments require to function. Beyond the heliopause, the Sun's contribution to the thermal balance drops to near zero. A spacecraft in interstellar space receives essentially no external heat. Its only sources of warmth are its own internal power systems and the tiny trickle of energy from the cosmic microwave background. If the internal heaters fail, or if the power supply declines to the point where heaters can no longer be sustained, the spacecraft cools toward the ambient temperature of deep space. At 2.7 Kelvin, most materials become brittle. Metals that are flexible at room temperature can crack under stress. Lubricants freeze. Seals contract and develop gaps. Electronics cease to function long before reaching that temperature. Most spacecraft electronics are rated to operate down to roughly minus 40 degrees Celsius or minus 40 Fahrenheit. Below that, circuits malfunction. Batteries lose their ability to deliver current. And solder joints can fracture as different metals contract at different rates. The Voyagers manage this problem by using waste heat from their radioisotope generators to keep critical systems warm. But as the generators weaken, the available waste heat decreases. Engineers have already turned off heaters on non-essential components, allowing parts of the spacecraft to cool below their design temperatures. The margins are thin and getting thinner every year. Eventually, a critical component will cool below its operating limit, and when that happens, the failure will be permanent. There is no way to rewarm a frozen thruster line or a cracked circuit board from 15 billion miles away. For a crewed mission, the thermal challenge is even more severe. Human beings require a temperature range between roughly 60 and 80 degrees Fahrenheit to function comfortably. The habitat must be heated continuously for the entire duration of the mission. Every watt devoted to heating is a watt that cannot be used for communication, navigation, life support, or science. And in an environment where power is the most precious and non-renewable resource, the thermal demand is a constant drain on survival. There is one more environmental factor that deserves attention, and it is the one that receives the least discussion: the psychological environment. A crew traveling beyond the heliosphere would experience a form of isolation that no human being has ever encountered. The International Space Station orbits 250 miles above Earth's surface. Astronauts can see their home planet through the window. They can communicate with family and friends with only a fraction of a second of delay. They know that in an emergency, a Soyuz capsule can return them to the surface within hours. A crew on the Moon is farther, but Earth is still visible, still reachable, still close enough that the psychological connection to home remains intact. A crew on Mars is the first to experience something qualitatively different. Earth becomes a bright dot in the sky. Communication delays make real-time conversation impossible. The sense of isolation is real and documented in analog studies. But even at Mars, the crew knows they can return. The trip home takes months, but it is possible. Earth is still there, still waiting. Beyond the heliosphere, the psychological landscape changes in ways that are difficult to overstate. Earth is not just distant, it is gone. Not destroyed, not lost, but functionally absent from the crew's sensory and emotional world. The sun itself becomes just another star, indistinguishable from the thousands of others visible through the windows. The familiar constellations shift and distort as the spacecraft's vantage point changes. Every visual, auditory, and emotional anchor that connects a human being to their species, their history, and their home is gone. Communication with Earth, if still possible at all, is measured in days, weeks, or months of delay. A message sent to mission control will receive a response long after the sender has moved on to other concerns. Real-time conversation is a physical impossibility. The crew cannot call home. They cannot hear a familiar voice in real time. They cannot receive comfort, advice, or encouragement from anyone outside their small group. Studies of isolated populations, Antarctic winter-over crews, submarine personnel on extended deployments, participants in long-duration isolation experiments like Mars 500 consistently show elevated rates of depression, interpersonal conflict, sleep disruption, and cognitive fatigue. These effects emerge even in situations where the participants know the isolation is temporary and that they can be evacuated if necessary. For a crew beyond the heliosphere, the isolation is not temporary. It is the permanent condition of the mission. There is no evacuation. There is no return within any meaningful time frame if the mission is truly interstellar. The crew must maintain psychological health, group cohesion, and functional decision-making capacity for years or decades without any of the support systems that every previous human mission has relied upon. The historical analog most often cited is the long-duration sailing voyages of the 15th through 18th centuries. Those voyages lasted months or years, carried crews into unknown waters, and suffered from disease, malnutrition, and psychological strain. But even the most extreme of those voyages occurred on a planet where the crew could see familiar stars, breathe air, find land, and encounter other human beings. A crewed interstellar mission would have none of those anchors. The void is not just physical, it is psychological. And the damage it can inflict on a mind that evolved to live among others, under a blue sky, within earshot of other human voices, is a danger as real and as lethal as any particle of radiation. This is the environment beyond the heliosphere. Not empty, not peaceful, not a serene void waiting to be crossed. It is a space saturated with high-energy radiation that degrades electronics and damages DNA. It is laced with microscopic grains of dust that become projectiles at interstellar velocities. It is cold enough to crack metal and freeze circuits, and it is psychologically barren in a way that no human being has ever experienced or been tested against. None of these dangers arrive as a single dramatic event. There is no moment of crisis, no alarm that sounds, no explosion that forces a decision. Instead, each one works slowly, continuously, invisibly." End quote. The radiation accumulates dose by dose. The dust erodes surface by surface. The cold creeps inward, watt by watt, as the power fades. The isolation presses down day by day, month by month, year by year. And the most dangerous thing about all of them is that they are not separate problems. They are the same problem viewed from different angles. The problem is exposure, unshielded, unsupported, unrelieved exposure to an environment that is hostile, not because it attacks, but because it offers nothing, no energy, no protection, no resources, no warmth, no connection, no rescue. Inside the heliosphere, the sun provides all of those things. Not perfectly, not without risk, but enough to make space travel dangerous rather than impossible. Beyond the heliosphere, the sun's gifts are gone, and what remains is the raw, unmodified environment of the galaxy. An environment that was never designed for life, never selected for habitability, never filtered through the lens of a protective star. It simply is what it is. And what it is, for any biological or mechanical system that enters it unprepared, is lethal. The only question left is what all of this means when you put it together. Because the individual dangers, as severe as they are, do not capture the full picture. The full picture emerges only when you see how they compound, how the loss of power accelerates the loss of thermal control, how the loss of thermal control accelerates the degradation of electronics, how the degradation of electronics accelerates the loss of communication, how the loss of communication eliminates the possibility of repair, how the impossibility of repair makes every subsequent failure permanent, and how the permanence of failure in an environment that generates new failures continuously through radiation, impact, and cold creates a trajectory that bends in only one direction. That trajectory, and what it reveals about the true nature of the danger, is where this story ends. Everything described so far, the power decay, the communication collapse, the navigation blindness, the radiation exposure, the micrometeoroid erosion, the thermal siege, the psychological void, each of these has been presented as a separate problem. A distinct hazard with its own physics, its own timeline, its own mechanism of harm, and that is how engineers study them. Individually, in isolation, one variable at a time. Because that is how engineering works. You identify a problem, you characterize it, you design a countermeasure, and you test it. But deep space does not present its dangers one at a time. It presents them all at once, simultaneously, continuously. And it links them together through a chain of dependencies so tight that the failure of any one system accelerates the failure of every other. This compounding is the real danger, not any individual hazard. The fact that they reinforce each other, feeding back into a spiral that no single fix can break, because the spiral is not driven by any single cause. It is driven by the one condition that underlies all of them: distance. Distance is not merely an inconvenience in deep space travel. It is not simply the reason communication takes longer or the sun appears dimmer. Distance is the mechanism through which every other danger becomes lethal. It is the force multiplier, the silent amplifier that takes each individual risk, any one of which might be manageable in isolation, and welds them into a compound threat that no spacecraft and no crew can sustain indefinitely. Here is how the compounding works. A spacecraft leaves the inner solar system. In the first phase, everything operates normally. The sun is distant, but still visible. Solar power, if the mission uses it, has already been replaced by nuclear power. Communication with Earth is delayed by hours, but the link is strong. Navigation corrections arrive regularly. The spacecraft systems are fresh, well within their design margins, operating the way they were tested to operate in laboratories on Earth. As the spacecraft passes beyond the planetary region and approaches the heliopause, the first layer of degradation begins. Solar energy, even as a supplemental source, drops to zero. The radioisotope generators are now the sole power supply, and their slow decline is already measurable. Communication delay crosses the threshold where real-time troubleshooting becomes impossible. If a problem occurs, the crew or the autonomous systems must handle it alone for hours before Earth can even be informed, let alone respond. The spacecraft crosses the heliopause. The heliosphere's protection disappears, cosmic ray intensity increases, the radiation dose rate to electronics, and, if present, to biological tissue, steps up to a new baseline that will persist for the remainder of the mission. The onboard shielding absorbs some of it, but not all, and the dose that gets through begins its slow work. Bit flips in computer memory, gradual degradation of semiconductor junctions, microscopic damage to DNA in every cell of every crew member's body. At this point, the compounding begins in earnest. The power system is weaker than it was at launch. It has lost tens of watts to radioactive decay. The spacecraft's thermal management system, which depends on electrical heaters to keep critical components within their operating temperature range, now has less energy to work with. The engineers, either on Earth or aboard the spacecraft, must make choices: which heaters to keep running, which components to allow to cool below their design limits. Each choice preserves one system at the expense of another. A component that is allowed to cool below its rated temperature does not necessarily fail immediately, but its performance degrades. A cold battery delivers less current. A cold thruster valve responds more slowly. A cold sensor drifts further from calibration. The spacecraft becomes slightly less capable, slightly less responsive, slightly less able to handle the next problem. And the next problem is always coming because the environment does not pause. Cosmic rays continue to strike the electronics. Micrometeoroids continue to impact the surface. The thermal gradient between the spacecraft's interior and the void outside continues to pull heat outward. Each of these processes operates independently of the others, but their effects converge on the same set of systems. The computer that must process navigation data is the same computer being bombarded by cosmic rays. The antenna that must transmit data to Earth is the same antenna being eroded by dust impacts. The power supply that must run the heaters is the same power supply that is losing 4 watts per year to radioactive decay. When one system degrades, it increases the load on the others. A computer that suffers more frequent bit flips requires more error correction cycles, which consumes more processing power, which generates more heat in some components and less in others, which changes the thermal profile, which affects the performance of adjacent systems. The chain of consequences is not linear. It is a web. Pull on one thread and the entire structure shifts. This is what engineers call cascading failure. Not the dramatic kind, where one explosion triggers another in a chain of fireballs. The quiet kind. The kind where each small degradation makes the next small degradation slightly more likely, and the cumulative effect, over months and years and decades, is a spacecraft that slowly loses the ability to maintain itself. In the inner solar system, cascading failure is manageable because the support architecture provides a backstop. Mission control can detect the early signs of degradation through telemetry. Engineers can upload software patches, adjust operating parameters, switch to backup systems, and in some cases send replacement hardware. The cascade can be interrupted by external intervention. Beyond the heliosphere, there is no external intervention. The cascade runs unopposed, and the further the spacecraft travels, the faster it runs, because every additional astronomical unit of distance weakens the already failing communication link, reduces the already declining power budget, and extends the already impossible repair timeline. This is why deep space travel is not simply a bigger version of the spaceflight we already know how to do. It is a fundamentally different condition. Inside the solar system, the support architecture bends but does not break. The margins narrow but never quite reach zero. Beyond the solar system, the margins reach zero and keep going. The support architecture does not just bend, it collapses, and once it collapses, every system on the spacecraft is running on borrowed time, consuming reserves that cannot be replenished, degrading in ways that cannot be reversed, approaching failure thresholds that cannot be reset. Now consider what this means for the proposals that exist, right now, for missions beyond the solar system. Breakthrough Starshot is perhaps the most well-known interstellar mission concept currently under active development. Announced in 2016 with funding from the Breakthrough Initiatives program, the concept envisions using a ground-based laser array to accelerate gram-scale probes to 20% of the speed of light. At that velocity, the probes could reach the Alpha Centauri system, roughly 4.4 light-years away, in approximately 20 years. The concept is ingenious. By making the probes extremely small and light, the energy required to accelerate them becomes achievable with technology that is within reach, at least in principle. The probes would carry miniaturized sensors, cameras, and communication systems. They would fly through the Alpha Centauri system, collect data during a brief flyby, and transmit their findings back to Earth using tiny onboard lasers. But even this elegant concept runs headlong into the compounding dangers of distance. At 20% of the speed of light, the probes would traverse the interstellar medium at roughly 60,000 kilometers per second. At that velocity, the micrometeoroid problem is not a chronic risk, it is an acute one. A dust grain, 1 micrometer across striking the probe at 60,000 kilometers per second would release energy comparable to a small explosive device. The interstellar medium contains roughly 1 dust grain per 100,000 cubic meters. Over a journey of 4.4 light-years, the probe would pass through a column of space containing thousands of potentially destructive particles. The probability of a mission-ending impact is not negligible. It is a central engineering challenge that has not been fully solved. The communication challenge is equally daunting. A gram-scale probe cannot carry a large transmitter. The onboard laser would need to send a signal across 4.4 light-years back to Earth, where it would be received by a collecting array. The signal strength would be extraordinarily faint. Detecting it would require antenna or telescope arrays of a scale that does not currently exist. And the data rate would be so low that transmitting even a single high-resolution image could take years. Breakthrough Starshot acknowledges these challenges. Its proponents describe it as a long-term research program, not an imminent mission. The technology required for the laser array, the sail material, the miniaturized electronics, and the communication system is still in development. Estimates for a potential launch date range from the mid-2040s to the 2060s, if the technical challenges can be overcome. But notice what the concept reveals about the nature of interstellar travel. Even the most optimistic, most technologically creative proposal for reaching another star involves probes so small they carry almost no instruments, traveling so fast they cannot stop at their destination. With communication so faint, it may take years to confirm whether the mission succeeded. And these probes are expendable. They carry no crew. They have no need to survive the journey intact. They are designed to collect a few seconds of data during a high-speed flyby and then continue into the void forever. This is the best-case scenario for interstellar travel with near-future technology. Tiny, disposable, barely communicative probes that may or may not survive the crossing. The gap between this and any crewed mission is not a gap that clever engineering can bridge. It is a chasm defined by physics. For a crewed mission, the requirements are orders of magnitude more demanding. The spacecraft must sustain a human crew for decades or centuries with all necessary food, water, air, radiation shielding, thermal control, power, spare parts, and medical capability on board from departure. It must maintain mechanical integrity over time, scales no human-built machine has ever been tested against. And it must support the psychological health of a crew that will live and die further from any other human being than anyone has ever been in the history of the species. No credible engineering study has concluded that a crewed, interstellar mission is feasible with current or near-term technology. The concepts that exist, generation ships, sleeper ships, fusion-powered vessels, are speculative frameworks, not engineering designs. They illustrate possible approaches, but do not solve the fundamental problems. The energy required to accelerate a crewed habitat to even a small fraction of the speed of light exceeds the total energy output of current human civilization. The mass of consumables required for a multi-century voyage exceeds anything that can be lifted from Earth's surface with existing launch systems. The reliability required of the spacecraft systems over centuries of continuous operation exceeds anything that has ever been demonstrated in any engineering domain. There is a concept that emerges from all of this that deserves a name, because it is the central truth of this entire story. Call it mission autonomy by necessity. Every space mission in history has operated with some degree of connection to Earth. Even the Voyagers, at the extreme edge of communication range, still receive commands, still transmit data, still benefit from the expertise of a ground team that monitors their health and makes decisions on their behalf. The autonomy of the spacecraft is partial. It handles routine operations and emergency safe modes on its own, but the strategic decisions, what to observe, which instruments to prioritize, how to manage the declining power, are made by human beings on Earth. Beyond a certain distance, this model breaks. The communication delay becomes so long and the signal so weak that Earth-based decision-making is no longer possible. The spacecraft, or the crew, must make every decision alone, not because they choose to, but because physics leaves no alternative. Mission autonomy, by necessity, is qualitatively different from the autonomy exercised by a Mars rover or a deep space probe. Those systems are autonomous within a framework established by their ground teams. They follow pre-programmed sequences, execute contingency plans designed by engineers, and wait for instructions when they encounter situations outside their programming. The ground team is always there, always reachable, always able to intervene given enough time. A spacecraft in interstellar space has no ground team, not in any functional sense. A message sent to Earth will receive a response years later if the signal is even detectable. By the time the response arrives, the situation that prompted the message will have evolved far beyond the point where Earth's advice is relevant. The crew must be their own engineers, their own scientists, their own doctors, their own psychologists, and their own mission control. They must solve every problem with the tools, knowledge, and materials they brought with them. Nothing else exists. This is not an impossible standard. Human beings are resourceful. They improvise. They adapt. The entire history of exploration is a testament to the human capacity to survive in conditions that should be lethal. But every previous feat of human endurance occurred on a planet. A planet with air to breathe, water to find, food to hunt or gather, materials to build with, and the possibility, however slim, of rescue or return. Interstellar space offers none of these. There is no air, there is no water, there is no food except what you brought, there is no material to build with except what you carried, and there is no rescue. None, under any circumstances, for any reason. The psychological weight of that knowledge is not something that can be trained away. You can prepare a crew for isolation. You can screen for resilience. You can provide counseling protocols and group dynamics, training and pharmaceutical interventions for depression and anxiety. But you cannot change the fundamental reality that every member of that crew knows with absolute certainty that if something goes catastrophically wrong, no help is coming, not today, not tomorrow, not ever. This knowledge changes people. It changes how they assess risk, how they respond to conflict, how they process grief, how they make decisions under stress. The research on long-duration isolation consistently shows that the awareness of being beyond rescue is itself a psychological stressor, separate from and in addition to the physical conditions of isolation. People who know they can be evacuated behave differently from people who know they cannot. The latter group shows higher rates of withdrawal, fatalism, and impaired judgment. A crew beyond the solar system would carry this awareness for the rest of their lives. Every morning, every decision, every crisis. The knowledge that they are alone in the most complete sense that word has ever carried. And that knowledge would interact with every other stressor, the radiation, the confinement, the monotony, the physical deterioration, the slow degradation of the ship around them, to create a psychological environment that no human being has ever been tested in and that no simulation can fully replicate. Let us return one final time to the Voyager probes. Because their story is not just an illustration of the dangers, it is a prophecy. Voyager 1 is now approximately 173 astronomical units from the Sun. It is the farthest human-made object in existence. In November 2026, it will reach a distance of 1 light day from Earth. Its power supply is fading. Its instruments are shutting down one by one. Its communication link is a whisper that requires the largest antennas on Earth to detect. Its thruster lines are clogging. Its computers are running on hardware designed nearly 50 years ago, hardware that has been bombarded by cosmic rays for decades, that is operating in temperatures far below its design specifications, that is maintained by a ground team that can only communicate in 2-day round trips. And Voyager 1 has not left the solar system. It has crossed the heliopause. It has entered the interstellar medium. But it is still gravitationally bound to the Sun. It is still inside the Oort cloud, or at least inside the region where the Oort cloud is believed to begin. The true edge of the solar system, the point where the Sun's gravitational influence gives way to the gravitational influence of other stars, is still tens of thousands of astronomical units away. At Voyager's current speed, that crossing is 30,000 years in the future. 30,000 years. Voyager 1 will spend 30,000 years inside the solar system after crossing the heliopause. And during every one of those years, its power will continue to decline. Its systems will continue to degrade. Its structure will continue to erode. Long before it reaches the outer edge of the Oort cloud, Voyager 1 will fall silent. Its generators will produce too little power to run even a single instrument. Its heaters will fail. Its electronics will freeze. Its antenna will point at nothing in particular, because the thrusters that aimed it will have exhausted their fuel or frozen solid, and then it will drift. A silent piece of metal and silicon, carrying a golden record that no one will play, etched with images that no one will see. Traveling at 38,000 miles per hour, through a darkness so complete that the nearest star is a point of light indistinguishable from a billion others. It will pass through the Oort cloud without knowing it. It will exit the solar system without ceremony, and it will continue into the interstellar void for millions of years, slowly cooling to the background temperature of the universe, becoming as cold and as inert as the space around it. This is what leaving the solar system looks like, not the dramatic departure that Hollywood imagines, not the triumphant crossing of a frontier. A slow, quiet, irreversible process of diminishment, systems failing one by one, connections severing one by one, capabilities disappearing one by one, until what remains is not a spacecraft in any meaningful sense, but an artifact, a monument to the ambition that launched it and the physics that defeated it. And here is the truth that sits at the center of this entire story, the truth that is more unsettling than any individual danger we have described. The danger of leaving the solar system is not radiation, it is not micrometeoroids, it is not the cold, it is not the loneliness. Those are symptoms. The danger is distance itself. Distance is the disease. Everything else is just how the symptoms present. Distance is what weakens the power supply, because no power source lasts forever and no resupply is possible. Distance is what destroys communication, because signals fade with the square of the range, and the speed of light is finite. Distance is what eliminates repair, because no rescue vessel can reach you and no spare parts can be sent. Distance is what strips away the heliosphere's protection, because the sun's magnetic bubble has a boundary and you are crossing it. Distance is what intensifies the radiation, because the further you travel from the sun's shielding, the more exposed you become. Distance is what makes every failure permanent, every decision irreversible, and every mistake fatal. And the most frightening thing about distance is that it does not feel dangerous, it does not announce itself. A spacecraft leaving the solar system does not pass through a region of turbulence or a belt of obvious hazards. The transition is smooth, gradual, almost imperceptible from one day to the next. The sun gets a little dimmer, the signal gets a little fainter, the power gauge drops a little lower, the temperature reads a little colder. Each day is almost identical to the one before it. The changes are so small that they barely register, but they compound, day after day, year after year, decade after decade. The small changes add up. And by the time the cumulative effect becomes unmistakable, by the time the power is critically low and the communication link is breaking and the systems are failing faster than they can be repaired, it is far too late to turn back. The distance that created the problem is the same distance that prevents the solution. You cannot retreat faster than you advanced. You cannot undo years of travel in a moment of crisis. The trap closes slowly, but it closes completely. This is what most people do not understand about leaving the solar system. They imagine the danger as something out there, a thing you might encounter, an obstacle you might hit, a monster you might face. But the danger is not out there. The danger is the out there. The distance itself. The separation from everything that makes survival and recovery possible. The growing gap between you and the only star, the only planet, the only civilization that has ever kept you alive. Every meter you travel away from the sun, you lose something. A fraction of a watt of available energy, a fraction of a decibel of signal strength, a fraction of a degree of thermal stability. A fraction of a percentage point of rescue probability. No single loss is noticeable, no single loss is fatal, but they never stop accumulating. And they never reverse. The solar system is not just a collection of planets orbiting a star. It is a life support system. The sun provides energy, the heliosphere provides shielding. Earth provides communication, navigation, repair capability, and the psychological anchor of home. Together, these elements form the architecture that makes human spaceflight possible. Not easy, not safe, but possible. Leaving the solar system means leaving that architecture behind, all of it, permanently, and stepping into a condition where the architecture does not thin out or weaken or become intermittent. It vanishes. Absolutely, totally, without replacement and without appeal. That is what makes leaving the solar system more dangerous than most people think. Not because there is a hidden monster waiting in the dark. Not because interstellar space is filled with dramatic perils that science fiction has not yet imagined, but because the most ordinary, most fundamental, most overlooked force in the universe, the simple fact of being far away, turns out to be the most lethal condition a spacecraft or a human being can face. The sun does not chase you when you leave. Earth does not reach out to pull you back. The heliosphere does not stretch to follow you into the dark. They stay where they are, and you move away from them. And with every passing hour, the distance between you and everything that ever protected you grows a little wider, a little quieter, a little colder, until eventually the distance is all there is. And in that distance, in that silence, in that cold, the true nature of leaving the solar system reveals itself. Not as adventure, not as exploration, not as the next great chapter in the story of human expansion, but as a slow, irreversible crossing into a condition where the universe is no longer indifferent to you in the way that a desert or an ocean is indifferent. It is indifferent to you in the way that the space between galaxies is indifferent, completely, structurally, without exception and without mercy. The farthest human-made object in existence is a small metal spacecraft that weighs roughly as much as a compact car. It carries a golden record that no one will ever play. It is running on a power supply that will be dead within a decade. It is communicating with Earth through a signal so faint that the entire energy it delivers to NASA's largest antenna would not light a single photon on your phone screen. And it has not even left the solar system. That is not a story about triumph. It is a story about scale, about the difference between what we can imagine and what physics allows, about the distance between the harbor and the open ocean, and about what happens to every vessel that sails far enough to lose sight of the shore. The shore does not follow you. The light does not chase you. The warmth does not reach you. And the distance, patient and absolute and older than every star in the sky, simply waits. It does not need to do anything else.